So let's talk about AI. We all know it's incredibly powerful, right? But it also has this weird hidden weakness. It can be surprisingly fragile, and that brings up a huge question. How can we ever really trust these systems? Well, today we're diving into two fascinating research papers that suggest the answer lies in a totally different way of looking at AI, not as code, but as complex geometric shapes.
Okay, so here's our game plan. We'll kick things off with this big trust problem. Then we'll get into how we can actually think about AI decisions using geometry. From there, we'll look at how one paper measures a network's raw power, and then how a second paper uses that same idea to, keep it in check. It's all leading us toward building AI we can actually rely on. Let's jump in.
So first up, this central paradox of modern AI. I mean, these models are just mind-blowing. They can generate art, help discover new medicines, you name it. But beneath all that power, there's this hidden brittleness, a fragility that creates a massive trust issue, especially when we start using them for really important real-world stuff.
And this quote from one of the papers we're looking at it nails it. This isn't some academic thought experiment. It's a real and growing threat. As AI gets woven into things like medicine or self-driving cars, this brittleness stops being a funny quirk and starts being a critical safety problem.
And this slide, this is the perfect example of what we're talking about. On the left, you've got an AI looking at a picture, and it says, yep, that's a panda, with super high confidence. But look at the right. Someone has added a little bit of digital noise, stuff that's totally invisible to you and me. But now the AI confidently says, oh, that's a gibbon. This is what's called an adversarial example, and it shows just how easy it can be to completely fool these incredibly smart systems.
So, how do we fix this? How do we build systems that aren't so easily tricked? Well, the researchers behind these papers suggest we need to change our whole perspective. To understand and control an AI, we need to understand the geometry of its decisions. We kind of have to learn to see the world the way it does.
Okay, so at their core, a lot of the neural networks we use today are what you'd call piecewise linear functions. Now, I know that sounds super technical, but the basic idea is really simple. Just imagine building something incredibly complex by stitching together millions and millions of tiny, simple, straight-line pieces. That's basically what a neural network is. And this is what it looks like from that geometric view. Imagine this huge space of all possible inputs, like every photo of an animal that could ever exist. A neural network's job is to carve that space up. It draws all these boundaries, separating it into different decision regions. Everything inside this one region gets the label panda. Everything over there gets gibbon. And that trick with the panda image, all it did was nudge the picture just enough to cross one of those invisible borders.
So this brings us right to our first paper, which asks a really fundamental question. If a network is essentially drawing this incredibly complex map, is there a way to measure just how complex that map can get? Could we measure a network's power by just counting the number of regions it's capable of creating? Now, this first paper zooms in on a really powerful type of network called a max-out network. They're a more flexible version of the super common ReLU networks. And that flexibility means they can create extremely complicated decision boundaries. In other words, they can draw a very, very detailed map.
And here's the key idea. The individual countries or zones on this decision map are what researchers call linear regions. And the total number of these regions isn't just some random number, it's a direct measurement of how complex a network can be, its representational power. More regions means a more powerful, more expressive network.
And this is the huge breakthrough from that first paper. They didn't just estimate or guess. They actually derived what's called a sharp upper bound. It's a precise mathematical formula that tells you the absolute maximum number of decision regions a specific max-out network could ever possibly create. For the first time, we have a way to put a hard number on a network's maximum potential complexity.
So, being able to measure this raw power leads us to the next, absolutely critical question. Knowing the theoretical maximum is one thing, but how do we make sure a real, trained network actually behaves the way we want it to? How do we get control? And that question is the perfect bridge to our second paper and this whole concept of neural network verification. Verification is all about moving beyond just testing an AI. It's about providing mathematical proof that it's going to behave correctly, not just on one input, but across a whole range of them. So as it says here, verification gives you provable guarantees. This means for a specific range of inputs, like say our panda picture, plus any possible noisy changes up to a certain level, we can prove that the network's output will always stay inside a safe boundary.
we can prove it can't be tricked into calling it a gibbon.
A really easy way to think about this is like building a fence. We can mathematically figure out all the possible answers an AI could give if we wiggle the input around a little bit. This cloud of possible answers forms a shape. If we can build a fence around that entire shape and prove that the fence never ever crosses into a danger zone, like the gibbon region, then we know the AI is provably safe for that input.
So if verification is all about building a good fence, then obviously the next question is, what's the best material to build it out of? And that's the key innovation in the second paper, using a much more sophisticated geometric shape to build a way smarter, way tighter fence.
This slide makes the comparison perfectly. Older methods often used simple shapes called hyperboxes. Think of that like a generic, one-size-fits-all square fence. It's easy, but it's often a really loose, sloppy fit. The new approach uses something called a zonotope. This is like a custom-fit fence. It can wrap much more tightly around the AI's possible outputs because it can actually account for how different neurons are related to each other.
Now, without getting bogged down in the geometry, a zonotope just hits this perfect sweet spot. It's flexible enough to create that really tight fit we want, but it's still simple enough that we can work with it pretty efficiently. So we get much better precision without our computers grinding to a halt.
The researchers built this idea into an algorithm called Zonodual, and, well, the results really speak for themselves. As you can see, it gives you much tighter bounds, which means more accurate safety guarantees. It's faster, and it can scale up to the massive networks we use in the real world. And it cleverly combines a couple of different strategies to give you the best of both worlds. Okay, so let's pull all this together. On one hand, we have a paper that gives us a tool to measure a network's theoretical power. On the other, we have a paper that gives us an efficient tool to control its actual real-world behavior. It's really a story about uniting power with control.
Together, these two geometric approaches really give us two pillars for building trustworthy AI. The first step, from paper 1, is to measure and understand the complexity you're dealing with. And the second step, from paper 2, is to efficiently verify and control that complexity once you've actually built something. You absolutely need both if you want to build systems that are not only powerful, but also safe.
At the end of the day, here's the big takeaway. This geometric point of view gives us a new, much more rigorous way to engineer AI. By measuring a network's absolute limits and then using these sophisticated geometric fences to verify its behavior, we're moving from an era of just kind of building AI through trial and error to an era where we can engineer it with provable guarantees of safety and reliability.
And that leaves us with a final, really big thought. As these tools for measuring power and verifying behavior get better and better, are we finally getting close to a future where trustworthy AI isn't just a goal we hope for, but something that is actually a mathematical certainty?